Thank you, Professor Saiful Amin, for the opportunity. So today I will be discussing and continuing on from Professor Sanada's part. This is chapter 3, target structural components to be seismically retrofitted. And I will be discussing about section 3.1, exterior beam column joints, and my colleagues will be carrying on for the later parts. So to begin with, exterior beam column joints with an insufficient anchorage has a potential of exhibiting pull-out failure, as shown by Professor Sanada earlier. So what is considered as an exterior beam column joint? If we consider this building frame, this rightmost column is considered as an exterior beam column joint because beam ends at this part. However, the leftmost column is not considered as an exterior beam column joint because beam extends beyond the column range. So why this happens is because of lack of proper anchorage in the beam to the beam column joint. So such kind of failure mode already shown by Professor Sanada earlier. In this section, we can actually retrofit this kind of potential risk of anchorage failures by installing RC reinforced concrete wing walls to the joint. How do we do that? We can install a wing wall in the interior side of the exterior beam column joints, and that will be sufficient enough to provide enough structural integrity so that this kind of brittle pull-out failure doesn't happen and change the failure mechanism to another types. So RC wing walls are among one of the most popular retrofitting techniques that's applied to RC buildings in Japan. However, they are mainly used to increase the column strength or the member strength along which is retrofitted with. But on this project, we focused on improving the structural integrity of the joint using this kind of wing wall. So we only install the wing wall on the interior side of the column. We don't do it on the exterior side. So the scope of this chapter or section is limited to the exterior beam column joint. The structure is constructed between 1995 to 2006 or later, in which in local markets of Bangladesh, reform bars were used, and development length requirement become a little bit less stricter than plain bars. So these are the scope limitations for this kind of application, and straight anchorage is assumed to be used because you cannot confirm that after the construction of the building. This part can be an assumption, engineering assumption. So for the judgment of the retrofit, as discussed by Professor Sanada earlier, that if the building's deformation is expected beyond the F limit. So what is the F limit? F limit was determined as 2.2 on the previous guideline explained under this project. So it's an evaluation process where a series of tests was conducted and found that at a drift angle or deformation angle of 1.5%, this kind of pull-out failure initiated. So if we limit the building performance up until this portion of deformation limit of 1.5%, then the building will not reach to a point or deformation point where this kind of failure exists. So that imposes a F limit of 2.2 according to this guidelines, according to this project's another guideline, evaluation guideline. So if that's the case, we will go on to the part here. If the deformation is expected to be beyond the F limit, we will first judge if a retrofitting is needed or not, and then proceed with the following retrofitting technique. So what's the technique here? We install the wing wall, but how do we determine the length of the wing wall? So we can determine the length of the wing wall using this simple equation where LW is the length of the wing wall and LD is actually the required development length for the reinforcement bar. This can be calculated as per in BNBC, which is almost similar to ACI 381, and EXLD is the existing development length. So for the case after construction, if we don't know what is the value of existing development length, we can use or assume it to be the 2/3 the depth of the column, which is a conservative estimation to come to a conclusion with the discussion with expert engineers from Bangladesh. So under this project, a series of two 70% scaled specimens were constructed and tested. Specimen J1 incorporating deform bar and also straight anchorage, as can be seen here. No hooks were provided, were constructed using low strength concrete, incorporating brick chips, representing the poor Bangladeshi building conditions, not the good ones, but the poor Bangladeshi building conditions. And specimen number 2, which is J1W, it's actually retrofitted specimen J1 with additional wing wall in the interior side of this. And the length of the wing wall was determined by this design equation formula. And specimen was loaded in such kind of loading frame where lateral loading was provided with horizontal jack. This is the lateral loading cycle from 0.25% to up to plus and minus 4%. And also a constant axial load was provided in the joint with the help of these 2 vertical jacks. This is the result of specimen J1, which was the benchmark specimen without any retrofitting, and also straight anchorage was being used. As we can see in the negative direction, after attaining maximum strength at 1.5%, a sudden drop in load carrying capacity was observed, and which was also followed by loss in reverse strain, which confirms that the initiation of pull-out failure point was at this point, which was 1.5% rift ratio, converting this to a ductility limit of 2.2, which was used as to impose the F limit for the structure. As we can see that this is the condition of the joint, and in the positive loading direction, which is this one, there was a joint shear failure, and the cracks extended along the diagonals and exterior longitudinal reinforcement of the column. However, on the negative side, this side, as we can see, there's a large vertical crack indicating that the beam section completely came out of this joint. So this kind of joint will not transmit any load through this part. So it's completely lost its structural integrity. What happened after we retrofitted this with the wing wall? This is the result of that case. As we can see that maximum strength was attained at 1.5% and minus 2% respectively. However, no significant drop in load carrying capacity was observed up until plus and minus 3% rift ratio. Why is that important? Because according to previous PWD guidelines, the maximum range of the deformation capacity of the building is taken as F max of 3.2, which represents to a 3% deformation ratio. So what we can say is that if we retrofit this kind of poor joint with wing wall, there is no requirement to impose that F limit of 2.2 here, because throughout the entire range, which is considered in the PWD manuals, it doesn't lose any strength carrying capacity, as can be seen from this test result. And this was the image of that test result. As we can see in the beam column joint area, there was no significant damage, and the damage was basically moved to the beam end by a failure mode of flexural shear failure of beam. So how to identify the failure mechanism in this kind of retrofitting process? So joint strengthening using this method will be sufficient to prevent pull-out failure as shown, and also joint shear failure. The prevention of those failure modes affect the failure mode and the shear resistance of the existing column connected to the joint. And the column failure mode is identified as the minimum of the two, CWQMU, which is the flexural resistance of column with wing wall, and CWQSU, which is the shear resistance of column with wing wall. These are already explained in the previous guidelines, PWD guidelines, and we can just follow those guidelines to determine the capacity of this. And finally, for the strength index and ductility index, CNF index, we can follow similar procedures explained in previous PWD manuals, which are CNCIP, BSPP, and also SATREPS-TSUIB evaluation manual as shown earlier. That's all from me. Thank you very much.